Mario, I had a question about this paper.
Yes, please.
Uh, could it not be that this cloud is formed because we are averaging over 100,000 points and those
You're
are
not
random
averaging
points?
over 100,000 points. You're averaging over uh, the number of neurons they have, which I think here in this case is 500 per point. So it's 500
Okay.
neurons per point.
But could it not be that we are always around zero point 0.5, not because we have
You
and since
is
they're all
yeah.
between 0 and 1, then of course the average is 0.5.
Well, sure, sure. I mean, so you have a sigmoidal network, and the sigmoidal network is talking, the different neurons are talking to different neurons, and they're averaging each other's activity out. So you will have some neurons that will have high activity at some points, and some other neurons will have low activity at some points. And so the grand average is close to 50%. But what you
Yeah.
should be thinking is that in every single point there, in every single point in state, many neurons will be highly active, and many other neurons will be highly inactive. And the types of neurons that will be highly active over time, it's not haphazard. If this was a random selection of states, if for every time step you selected a random number for each single neuron, therefore creating a complete, random selection of 500 numbers, then you will not have a point cloud that is as structured like this manifold. You would have a point cloud that looks like a sphere, uh, or a circle, really, full of points. Does this make sense to you?
But then I wanted to ask, how is the so here they're showing t and t plus 1, right?
Yes.
Um, t plus 1 another completely random selection, or is it
No,
adjusted
it's a
according
next
to
step from the network. So the network is discrete time.
yeah, and the next step, does it have some kind of learning rate that is small? Because I would imagine that if the learning rate is small, then the
There's
next
no
step
learning
is
rate
obviously
here.
okay. So I don't get how they go to the t plus 1. Is it only Hebbian?
There is no t plus one is only activity of the network. There is no Hebbian. There is no learning in this graph. There is no learning. So in this graph, you have the activity of 500 neurons average. That's going to be your x-axis,
Mm-hmm.
and the average activity of the 500 neurons in the next time step. That's your y-axis.
There is no relation between t and t plus 1.
T plus one is one plus t.
Yeah, no, I mean, so the activity at time t, does it affect the activity at time t plus 1
But of
somehow?
course, you have a state and you have a randomly recurrent neural network. So basically, what you do is you have this state of 500 neurons. Can you guys all imagine what 500 neurons state look like? So basically, these are 500 numbers between 0 and 1 because we're talking about sigmoidal units, right? And that's a state of activity. Good questions. Thank you for the questions because I think they help other people too. So 500 neurons. These 500 neurons are going to go through a randomly recurrent neural network, but it's only one structure. We've randomized the connectivity, we've randomized the weights, the strength with which every two neurons are connected is random. Is like when we created random networks back in our adjacency matrix project, and you multiply by the state vector. So t plus 1 is activity of t times the weight matrix wrapped around the sigmoidal nonlinearity. And before you tell me you understand, I will not move forward.
No, I said it was okay, just my connection kind of crashed for a second.
Don't worry. No, no, it's these questions are very good. So I hope now that more of you have got the idea that every single point here in this point cloud is showing the future as a function of its past, immediate step. So it's immediate discrete step in the future. That's why, like just before that slide, we had talked about propagation. So here, we have simply propagation without the sigmoidal function, but the idea is that when you have a randomly recurrent neural network that is in discrete time, the activity in t time plus 1 is a function of the activity at t times the connection that you had before. In this equation, we're missing the nonlinearity. We're only talking about the propagation. But the idea is the same. You're plotting a t plus 1 of the average activity, so average activity of a of t plus 1, as a function of a activity in t. The average of all neurons in t plus 1 against the average of neurons in t. Better? Yes? No? Other questions? It's good to understand this paper because it's one of the most simplified versions, and it's going to come back soon in the context of reservoir networks. The idea here is that if you randomize the weights between these neurons, and you have a random initial condition, the portion of phase space, and remember what phase space was? Phase space was a place where you plot the state variables of a dynamical system. So the phase space is the places where the activity of your neuron can occupy. And a priori, they can occupy any position, like you said, between 0 and 1. So what you would see here is that the network is kind of balanced. That's why the average is close to the 50s. But we also see that this cloud is very structured. It's not a random cloud. It's not the opposition here would be if you have a complete uniform distribution of states. That would tell you that the highest likelihood of you going from one place to the other doesn't inform you what the future is going to look like. But because you see these darker areas, that means that states like to go there. And so if you had a state here where my cursor is, in the next time point, it will be here, which is more or less the same place, actually. So it looks a little bit like a region that is attracting. But compare. Here we have an average activity at about 0.54, but in the next state, the network will have an activity about 0.51. So it's going to be over this region of the cloud. So these attractors are going to be, or these states are going to be jumping between different parts of this chaotic attractor. I didn't call it yesterday chaotic attractor because I don't want to bring too many things, right? You actually don't need to bind it with a word. But the point is that this is a set of states towards which the network wants to tend to. The thing to keep in the back of your mind is a default network in the brain. A default network in the brain is, well, the brain is connected in functional ways, lovely, I mean, perfect anatomy, and you're not thinking about anything in particular. Your thoughts are jumping around. They're jumping around, but they're jumping around in connected ways. But they're jumping around. The places where your thoughts can occupy, the set of activities that your brain areas will have, will be related to this attractor cloud. So this is the conception of most people that are thinking about default networks in brains. This is the kind of image they have in the back of their minds. Even though this is a highly simplified model, it doesn't have different kinds of neurons. The time is discrete. We're going activity state to activity state. The adjacency matrix is completely random. It captures that aspect of dynamic propagation of activity in brains. We're in the same page? So, kind of like a default network, a mini model of a default network. They didn't claim it was, but if you create default networks in the brain, like based on diffusion tensor imaging, you can actually probably look at that, because there's many models right now that are looking into the default network, and the quality of predicted activity is substantial. Although, one more thing to mention here in the last one is that in chaotic attractors, there's sensitivity to initial conditions. So if you start in points that are very close by, your trajectories can diverge in the future. Although this is a more involuted point. The idea that, even starting with a frozen state of the brain, just a little bit of stochasticity will lead you to different kinds of ideas, different kinds of memories. Or maybe sometimes it will take you to all that memory over and over again, whereas we can actually try to explain that with habit learning. Okay, I'll move forward now. Questions, thoughts? More neural dynamics, but now of randomly recurrent neural networks. This is the spirit for the entire lecture today, and I hope not to make it too long, because I think the lecture part's going to be about an hour, like from now plus an hour. Say like in half an hour I'll give a natural break, and then I'm coming back for another half an hour, and then we can focus on the project and on distributing ourselves around the literature. Neural dynamics. So attractors, neurodynamics, attractors, brain, attractors, neurodynamics. That's it. So there is a reason why we have converged into an understanding of the brain that leans so heavily on the word attractor. This has revealed itself to be a common interpretation to which many of the analogies we end up creating go to. Now we have to understand what they are, but in these minimal models we can see, the models I'm going to be talking about going forward, we can see how the pattern generation, such as motor pattern generation, you're brushing your teeth, okay? So you have a cyclic motion. So cyclic motion can be very well represented in an attractor. In fact, it will be a limit cycle attractor that you're engaging in with volition. And there's variation, but you're actually converging to that kind of oscillation. Spontaneous dynamics, just what we saw in the previous slide, spontaneous dynamics of random networks go to attractors in the sense that the activity can be characterized as following a certain set of states, a specific set of states. Encoding a sequence is well represented by attractors. Echo state networks are great in encoding sequences, and I'll show you how. Retrieving memories in the context of Hopfield networks, but even more complex networks that inspire themselves in the same general idea, can be related to attractors in the network. In the case of the Hopfield network, those are fixed point attractors. You have one state towards all initial conditions like to go, and they settle there. But they don't necessarily need to be fixed point attractors. They can be more complex attractors. And dynamical reservoirs is the idea that networks inside themselves have dynamical potentialities, things where they like dynamics that the networks like to have. So if you create actually this goes back to what I just said, if you create a brain, or if you take a brain and the brain is connected, you go and you insert a little bit of electricity on one via an electrode into your brain. That is going to create that's going to pump activity in your brain in structured ways. It's going to start here, and then it's going to talk to these first networks. And that's why when the clinician making an operation on the patient with epilepsy turns on his, I forget now, there was this beautiful anecdote. What was it? Okay. Friend of mine was talking about this clinician that started to during operation, to test whether that brain was still healthy, was giving some zapping, and then the person, started having an evoked memory, and I forget what it was, but it was funny. So some evoked memory that was funny. After the operation, apparently that person, in certain situations, when she went to the hospital, maybe, so the clinician inserted the electrode, pressed a button, the person thought about a banana. Next time, every time that she would meet the doctor, she would think about a banana. So she would retold this story, right? The idea is that you have the reservoir that when you create a perturbation in a structured way will create trajectories that have specific semantic implications. And these semantic implications can even be exercised multiple times in the future. But they're also more generally reservoir. As you're born, you're 2 years old, you have certain activities that your brain can have. I mean, like, even if it is not particularly functional, even if it's not connected with a banana. It will be eventually. So if attractors are this middle point in understanding what the dynamics of the brain looks like, what happens when we integrate the body into this part of the explanation? This is a picture that I've used some years ago to represent how the interaction between agent A and environment E are like creating a parameterization for a dynamical system. So a parameterization for a dynamical system is, for example, everything that comes into your sensory systems. If I'm here, I get this image, like I feel this proprioceptive feedback, and everything is structured. So all of the activity in my sensory sheets and my sensory systems is clamped to the posture and position that I'm in right now. So in a certain interaction with the environment, the perturbations from the environment create parameterizations in my sensory systems. That's what this equation on the top says. So over time, you have the interaction and the exchange between the agent and environment create parameterizations. For what? Parameterizations for what? So these inputs, rho t, that go through the sensory system, they're going into the recurrent neural network of your brain. Now it's a complex recurrent neural network, but still a recurrent neural network. When you push those parameters, like the clinician pushes the electrode into the brain, it creates the state of the recurrent neural network. And that state, that parameterization from the dynamical system's perspective, resolves a single dynamical system. So a single parameterization, given a recurrent neural network, imposes a certain set of dynamics on the network that you have. And that network will have a certain attractor structure. When I say attractor structure, the picture, again, you should have in mind, is something like this right panel here. It is a cloud of places where the network likes to be when it's parameterized in a certain way. Can be more or less functional. So this attractor structure then is pumped down onto the motor system. Other places too, and also recurrences in the brain, but it's pumped into the motor system. And the motor system, maybe if you're a 2-year-old child or 1-year-old more like, or a 3 months old, you will babble. Motor babbling is the idea that you have these gestures that don't make a lot of sense, but your brain has activity and your brain is wired to your body, and so the brain produces a hiccup because you have been parameterized by something, anything, and then woo, child is happy or child is sad, who knows? But this motor action is being produced more or less spontaneously from the organization of the recurrent neural network, which will change the relationship with the environment, thereby parameterizing the system again, and hence involving it in the loop.
Sorry, Mario, could you give an example of parameterization, for example, in a motor with?
Whoa, so you have a highly multidimensional parameter in your brain. Parameters are not state variables in the sense that parameters change a little bit slower than variables themselves. So let's talk about state variables like the M activation variable of the Hodgkin-Huxley or of your sodium channels. Those are state variables that are changing very quickly, every single millisecond. The interaction with the environment is changing slower. Your body moves slower into the environment. A parameterization will, for example, be And indeed, I mean, if you're thinking about input, you wouldn't be wrong. So it's the way in which the sensory data modifies the entry points of the sensory system. So parameterization would be, for example, the image that is coming into my eyes like right now. Or in the deep learning network, you would have, you know, maybe 4K images that you want to recognize. Those are 4K, 4,000. From the perspective of dynamical systems, those will be 4,000 times 4,000, so 60 million points, 60 million parameters. So 16 million neurons, 16 million parameters. The inputs to a neuron usually are looked as parameters. So if I'm sitting down on my chair right now, every single Pacini corpuscle that is being pressed into recognizing the pressure in my butt is activated, like with a certain probability, and that is changing slowly with respect to the dynamics of the system itself. That's a parameterization as well. That's why this is an abstraction of the system, right? So this is a dynamical system abstraction of what's happening in the loop. Criticisms, questions? Okay. This abstraction allows us to think about the networks as getting inputs as perturbations from the world and propagating those inputs from the world as the activity that transfers itself through the network. It's almost a tautology that it should be so. But because of this tautology, we can use the tools of dynamical systems, and they're powerful, to explain where the system is going. And this is just a slide to remind you of the kinds of tools that dynamical system has in mind. This is looking into a two-dimensional continuous system, just like the adaptive exponential integrated fire, for example, or any two-variable set of ordinary differential equations or rate equations. And in A, you have the vector field that shows where your state is going to go if it is at any given place. I mean, it's the local derivative of the state. So if you have two variables representing, for example, the position of a leg, and your leg is over here, then your leg will tend to go over here, or the activity of your leg will tend to converge onto this fixed point attractor. If, however, your leg is over here, it will engage onto potentially a limit cycle attractor just rotating around this other, probably a saddle node. In B, you see the phase portrait, so basically representative orbits of that dynamical system. In C, you see the Noke lines of the system, if you remember the Noke lines of the system. In D, you see a bifurcation diagram, and in E, you see a parameter space analysis. The parameter space analysis is changing the entire dynamics of the systems themselves. So the green regions, they contain sets of parameters that have similar phase portraits, such as in A and in B. If you go from green to blue, for instance, you might lose an equilibrium. If you lose an equilibrium, then your leg will no longer converge to this point here in B. It will potentially only engage into a limit cycle, such as what we talked about in the context of single neurons, but not only in the context of single neurons. And this is why I'm bringing this back. I was talking about dynamical systems in the context of the sensory motor loop. The agent and the environment are coupled. We talk about the organism as the agent. We have these tools that we can use and deploy. One lovely paper that has looked into this in the context of recurrently neural network controlled robots was this fairly seminal paper by Randall Beer, a dynamical systems perspective on agent-environment interaction. There's a reason why we use these words. Here on the bottom, can you recognize what's here? What these equations say? I mean, just looking at them, can you recognize all the parameters? Can anyone explain me what the equations say just by looking at it? Okay, what is y dot?
dy by dt.
dy by dt is the rate of change. Is the rate of change of the state variable y. Right? And we have two variables y, y1, y2. That's it. It's the change of y over time. So dy dt. And we use y dot because it economizes 4 different characters. So this is a continuous differential equation. And what is w11 and w21? So what does y represent, do you think, here? For example, neurons. For example, the activity of continuous time neurons. A common representation for EEG style modeling would look like this. Could also represent the activity of areas of the brain. And W1, and so these are two areas or two neurons that are connected via the weights W11, which is a self-connection of unit 1 to itself. Sigma, which represents the sigmoid, which is the nonlinearity that applies onto the incoming activity from itself. Minus theta, which is a bias. And then the connection that is coming from unit 2, W2, W21. So you have here a recurrent, small, simple network of two neurons, such as could be in a central pattern generator of the C. elegans, or the ganglia of locomotion of a stick insect. Beer has used this representation of neurons to try and control a little virtual insect. And here what you see is on the top left is the entire network, tau I, which is a little time constant for that network, y dot I, which is one of, say, a number of different neurons. And in this case, the network has 5 neurons, as you see here in the bottom. Per leg, it has 5 neurons. So the entire network has about 13 neurons. And these neurons are not spiking, they're continuous activity, just as the simplified ones that we were looking before. Only the difference between the discrete and the continuous is that one is a map from time to time, and here you have a rate that goes from moment to moment. And so you have this connectivity of the network here, and you see it in the graph. You could probably write the adjacency matrix for it. Could you write the adjacency matrix for this network here? It would be a lovely question for a difficult test. And you have a parameter, which is the angle sensor for the leg. And so since we're talking, it's a simple problem to start with, okay? So we're talking about an angle sensor where the leg is, each leg has its own sensor, some sort of proprioceptor. Then you have 3 motor output neurons, the foot motor output, the backward swing motor output, and the forward swing motor output. These are activating different muscles. And you should think that, you know, like the level of abstraction here, underlying these units, there will be maybe spiking neurons. They act like continuous because they are in a larger scale networks. So the entire 30 neuronal network of the stick insect is now displayed in B, where the individual connections between each area are like not overlaid so that it's not too dirty. But in principle, then you have a fully recurrent network for the 5 legs. And I will not tell you exactly how yet, but I'll tell you in a moment that he's obtained parameters, connectivities between these different motors and sensors and across the legs to produce the dynamical system trajectory that you see here in A on the right bottom. These are now the activation values of the neuronal units of a single leg in this stick insect. So you see that there is a velocity angle, then there's so this is the velocity of the insect itself. So A is not an activation. I lied to you. So A is simply the velocity of the insect. So basically the insect is going and then stopping. So it goes. But the foot, the backward swing, the forward swing, the interneuron A and the interneuron B, these are the 5 neurons that we see in the network. And they interact in a way to produce a sequence of activations such that the foot touches the floor. When the foot finishes touching the floor, the leg pulls back, the neuron, the extensor of the leg pulls back. Once you finish that, go forward, you lift your leg, and so or lift your foot, and so you create a gait. So basically what I'm saying is that you connect this recurrent neural network of each foot as such, and you can find parameters that will get the insect to walk. I don't have a video for this, but I'll have some other videos in a moment. But I want to show you now what this looks in terms of projecting to a lower dimensional space. So a projection to a lower dimensional space. We have 5 neurons in our network, 3 of which are motors: the foot, the backward swing, and the forward swing. The representation of the trajectory of the leg can be projected into the 3-dimensional space, indicating the activation of the 3 motors. And you see a limit cycle attractor that is the gate itself, the motor part. You're not seeing the extra 2 hidden units per leg, but you see here the entire phase space of the motor output of the 5-dimensional of the 5-dimensional attractor, of the 5-dimensional dynamical system from these 5 neurons that has been parameterized by its proprioception. This is what we mean when we say a projection to a lower dimensional space. We had 5 dimensions and now we have 3 dimensions. We can look at these 3 dimensions and we can make sense of them. So if you follow the trajectory, you will say, let's go with the easy one. So first, the activation of the foot goes to 0. So basically it rests. Then you have a forward swing, activation of the forward swing, which brings up also activation of the backward swing, which brings us back to a foot placement, and so forth and so on. So that what Sam was demonstrating is also like a nice little engaging on a trajectory of that can be represented lower dimensionally, right? You're doing like this. So so this is the kind of mindset you should have in mind when we're talking about kinematic studies. I'm reviewing a grant right now that is really fun. They're basically pumping a neural network into a robot, and the robot should shake your hand. And the robot will shake your hand in 2 ways. One like is very rigid, and the other one that is very, very gentile. So these 2, very gentle. So these 2 can be represented as attractors in a dynamical system and can be produced by such a network. So here's a representation of the entire phase space. You can see the tiny little where the leg is of the insect. So it's going forward, it's going backwards, going around. Okay, bum, bum, bum. A lot of our understanding of insect locomotion comes from these kinds of studies these days. Questions? So here is how so the point really being, you have one parameter, which is the sensor, the proprioceptive sensor of the leg of the animal, or the animat, as they like to call these artificial agents, that when coupled to a dynamical system that is coupled to the environment, engages on a loop that produces a trajectory that is a closed trajectory in certain cases, to then explain the gate formation via the neural network. That was the point of this set of slides. Yeah. Now, I might have shown you this slide before because it's just so good. Embodied behaviors. In the sensory motor behavior lecture, we talked about them. Is it clear what a parameter is, or a set of parameters is, or in fact a correlated set of parameters in the case, for instance, of the image of the optokinetic reflex? Right, so think about parameters here. Big things that are going through these organisms. They're not individual neurons firing, they're great masses of neurons firing. And they're engaging into oscillatory, most of them are oscillatory behaviors, not all of them. Or cyclic, repeatable gestures and behaviors. Not every time the same, but alas. So this is the sensory motor loop that we believe is underlying these kinds of activities. Give you an example of work in this direction. So actually, let me, maybe a video would help, because I don't have the video here. I have the video in YouTube, so I actually thought that the video was here. But this is a set of 3 embodied problems where you see little robots that are controlled via recurrent neural networks to achieve certain functional goals. And you will see what these functional goals will look like in a moment when we look at the video. But let's not get ahead of ourselves. So I want to present to you a set of evolved neural networks. Randall Beer's networks for insect walking are actually also evolved via artificial evolution. I'm going to give you an example of artificial evolution and embodied tracking in artificial evolution. And in my case, it's going to be an active tracking with a robot that looks around to follow an object. I'll show you the video so that you can see more clearly what I mean. But before I get there, I just wanted to go back to our ideas like that we had before, like genes and how does the whole thing come together? I mean, you have to think about the entirety of the motor action or motor behavior, as a set of levels whose interfaces are constraining each other. So the body posture will determine the skeletal constraints, the mass distribution of your body, inertial distribution, the muscle forces, the joint angles, which will be determined by the single cell contraction forces, the number of cells available to contract, the architecture of the muscle fiber, which will be determined by the amount of incoming activity, the rate of the activities of the networks, the cell's biochemical state, and so forth. These will be constrained by the activity of the networks at the level of the brain, and the innervation patterns at the level of the spinal cord, which will be then further constrained by the activity, the individual neuronal properties, the network connectivity, and incoming muscle and joint state. So in general, a muscle act crosses levels. And so you have to look into the muscle level, not as disembodied neuronal activity, because that's boring. You want to look at the neuronal activity as a direct function of its motoric consequences. In evolutionary robotics and neurodynamics, we are often thinking about these particular impositions. We start with the idea that behavior is controlled via recurrent neural networks. We use small ones because we want to be able to analyze them via the dynamical systems. In this case, I will show you an example of a discrete time recurrent neural network, which is the same one as you have in the simple neural network project and in many other, Hopfield-like and the propagation. And so you should be able to very quickly recognize this formula here, the first one. Can you? Can you say yes or no? Like if this formula, the first formula here should be like super ultra clear to everybody of you. Is it? Yes or no? I expected 2 yeses from these people. Yes, I expected a yes from you. Expected a yes from you too. Expected a yes from you. Is there anyone that wants to say no? No. Now the trick here is that we structurally evolve the connectivity and weights of these neural networks by having a fitness function, something that tells us that some agents with those neural networks are better than others. We do assume what are the environments within which these functions have emerged. And we analyze then the formed recurrent neural networks with the dynamical systems theory. To evolve those networks, we start with some sort of genotype, which could be, for example, a bit string 01000101. Then we need a developmental plan which transforms that bit string into your recurrent neural network. So it says, okay, when you have a 001, you put a neuron there. When you have a 010, you connect that neuron with that neuron. So basically you have a bit string, which is a genome, which then transforms your agent into a recurrent neural network. It puts that recurrent neural network in a body, in a simulated environment. And once you put a recurrent neural network in a body, it does something. It has some spontaneous dynamics, and it will interact with the environment. Sometimes better, sometimes worse, with respect to some sort of survival function, some sort of fitness function that we prescribe. We then assume that that fitness to the behavior, that quality of the behavior, is going to be the survival capability. Obviously, this is, I have a couple of caveats here, but this is the abstraction. Then you have a selection, which is, say, the 5% of the best acting robots, they're going to have children, and they're going to produce more bit strings that represent neurons. So you have a certain reproduction probability. You induce a certain variation, so some genetic operators. So crossover, you change the bit strings a little bit. Not a lot, because then you will break the behavior, but a little bit, so that you will have a slightly different set of recurrent neural networks in the next generation of genomes. And in the next generation of genomes, you create recurrent neural networks, and so forth, and so on. YouTube moment.
Can I interrupt for a second?
Of course you can.
What would a survival capability be in this context?
So it can be anything. Can be, for example, don't die out of energy. So some people have used the ability of foraging. So the longest you walk. So anything that, or the ability of having found food. So say, for example, your genome does not take you to a particular food source and you cannot feed, then you die. So our fitness function is going to be the amount of food that you've acquired. But maybe that's not sufficient. Maybe you will create another level. And you will say, okay, you have to have two things. First you have to move around. If you're not able to move around, we measure how many meters you're able to walk if you're a robot and you're embedded. And we measure your ability to feed yourself, some abstraction of the ability to feed yourself, which is, for example, getting close to a food source or tracking an object. So that was going to be the next point that I was going to give you right now, the fitness function that I've used for the robot that I'll show you in a moment. Embodied brain. So I probably have to go to the original videos because didn't create. Manage videos. These are old videos, so they're early in my channel, so I'll have to go a couple of days in back. I wanted to have prepared this, but I had to cook breakfast. Hello, YouTube. Do you see the moving bar saying that it's taking time? Oh, come on. Terrible. Broken. Okay. Okay. I'll not be able to show you all the videos because some of them are older. But here you have a cyber head. It's this sphere. It's an old video, so I'm sorry. Okay, so like I've done this screen capture in 2007. You should be surprised that it even is there. So this is an environment within which you have a robot. His neck is disconnected because I like things that float. But you should imagine that he has two motors. One that is able to do this motion up and down. So it has a certain span with a recurrent, with a restriction, a constraint, and should be able to do this motion as well. So yaw and pitch. Now the rays that you see are representations of 9 retinal inputs to that robot. Okay, so he has an eye with only simply 9 inputs, and his job is to follow the ball that is jumping randomly within this environment. This is a network that had been evolved through evolution. The first networks do not do this. They jiggle around, they go into a certain direction and stay. They're basically not functional. The fitness function in this case is the ability of the robot to keep looking at the object for a longer span of times. So you're basically summing over the sensor values of that robot. So red means he is looking at the ball, white means that sensor does not see the ball. Forgive me for the poetic licenses. So the neck doesn't appear connected. It doesn't need to be connected because ultimately there is a center point where the circle is implanted. And so you have two motors, one that is looking sideways and one is looking up and down. Wanted to show you one of the holonomic robots that I also have, so R2. I mean, maybe. Nope. Nope. I mean, like, unfortunately, I have to have a much better way of dealing with my own videos. But there's another pretty one that I wanted to show you because it shows also the variability in the different robots themselves. Let me try one more time to manage the videos, because then one more time. Okay, that's looking better. Here. So this is a robot mounted on 3 wheels, and his fitness function is also find the object and follow it. So basically move towards the object and absorb energy from it. It has different initial conditions, and it's able to then orient itself to find where the ball is. Different robots will have different strategies to follow or not follow the ball. So this is a long time ago. Is this getting to you? So the general idea here is that the robots have different qualities of the behaviors that they have. Over time, they're evolving these recurrent neural networks. The recurrent neural networks are connecting 9 input pixels with 3 rotating wheels and a head that can move up and down, left and right. The fitness function is this one in the bottom, which is the sum over the sensors. So simply saying, okay, the more you're able to feed, better you are, and then we're going to reproduce you. So that was your answer, Daphne. So Natia, then here on the determine alpha, this is the multi-objective function. Determine alpha is the sensory term that says you're able to feed. The term in beta is an energy term saying, like, if you overuse your motors, you're probably not doing so well. So you have to, it's an energy sparing term, which is subtracting the amount of movement across 2 time steps. But in any case, so they have a fitness, and because you go through this process through hundreds of generations, you eventually get robots that can do well. And here I think you have a better representation of what the sensory input are in figure 3 in the bottom. You can see the panels where the individual sensor values that the robot is acquiring when it's following the ball are doing. Okay, so ball is a bit up from respect to the eyes, ball is a bit up and left, ball is a bit left, ball is a bit down. How do you follow a ball? That's now a next question. How do you actually follow a ball? Well, how you follow any object. If it moves too far, you have to recenter it. If it moves too far in the other direction, you have to recenter again. So basically, it's a matter of fixation and centering for simple organisms. Super simple. No, I mean, so this is just the idea that you can, from small beginnings, you can explain behavioral bootstrapping. These networks have recurrent dynamical systems, maybe 50, 30 neurons, and via this input, they produce a projection to the motor space, just like in Beer's projection to motor space, whose average activity, they're oscillating, no, here. These are the 2 output motors in the figure 4. So one is oscillating up and down, the yaw output, and the other one is, so oscillating up and down means, in that case, because it's the yaw, it means that the robot is keeping his head fixed or oriented, because the amplitude of the oscillation on the left and the amplitude of the oscillation on the right cancel each other out. Whereas in the pitch output, you see that it spends more time like looking down. So the average activity of the neck of this robot when he's receiving this input on the left from the 9 pixels is look down. And this is the average action that the robot is doing. I remind you that when we're having our neck looking forward, we're probably having both muscles active. So here we have rigidity. And if we have rigidity, we also have a high frequency activation of the contralateral muscles to keep the head in place. So it's a little bit like you look forward, but you have activations in both sides. It's a little bit like what normal necks should look like. Another interesting thing, for very similar input states, you might have different attractors to which the network falls into. And so in the top layer, you have 4 presentations of the same stimulus. And for each column, you have a representation of the 2-dimensional attractor over time. Time is going in Z, and X and Y are the activations of the motors. These are the trajectories that the recurrent neural network adopts when it's presented with that stimulus. The attractors that the network takes are different, even though the stimulus are the same. It's because the network is more high dimensional. And in the bottom, we have here a certain direction that for every single one of these cases, for every single one of these attractors, the actual direction was the same. So you have a many to one projection from the dynamical system, from the attractor landscape onto the action. Let's have a look at the video that Miro shared with us. Natural selection. Seems cool.
Is about
8 million views, wow.
All right, so what does and we'll start seeing some natural selection of traits.
Yeah. Cool. So, save the video, watch it later. So this is also artificial evolution, and I don't know what the guys are going to do, but it's 10 minutes of fun that you can have later. Yeah. I'm showing you this old data because partly I think that it epitomizes some of the fundamental learnables here. The fact that these dynamical landscapes can be evolved as you're transforming the recurrent neural networks that are controlling the robot in the embedded loop. How do you look at all possible actions that a robot can do? If you look at each single neuron separately, if you put an electrode in each one of those neurons, they will happen haphazardly, and you're trying to find their tuning curves, and you're trying to find their receptive fields, and you find that they're correlating somehow with their action, but you don't really know what they're doing. Here in an artificial setting, what we can do is we can inspect the entirety of the space, but there's a catch. On the left plot, we have the activity of the up and down neuron, the average activity of the up and down neuron. The color is the average activity. So one will be red, will be look up. Blue would be negative, look down. So these are hyperbolic tangent neurons. Green will be, well, I don't really know what you're seeing. And if you are a dynamical systems guy, here you're seeing like these fringes here, and you're thinking, wow, so these are fractal basins of attraction. And yes, but never mind that. The idea here is that you have to plot the activity of the neuron as a function of the input, as a function of the sensory input. In order to find what the tuning curve of a neuron is, you have to present the stimulus that is meaningful to the robot. So here you have the relative ball position in the vertical as being our stimulus dimension, and the relative ball to the horizontal as the stimulus dimension. If you had taken a single neuron and just looked at one of the inputs, then this picture would not be so clear. The picture is clear, and it says, okay, when the ball is up and centered, you look up, because that's how you're able to follow it. This is the attractor landscape that entitles the paper. The idea here is that for every single pixel of input, you have a certain set of attractors that you can engage in, and all of the meaning of these attractors, the actual action that they're engaging in, are meaningful because they have been selected via evolution. So despite the fact that every single network from these robots is going to be different, and the activity for every single time you present the stimulus is going to be a little bit different, as in a point cloud, the invariances for function are necessary. So if you want to follow a ball that is to the right of your visual stimulus, then you better look right, because else it's going to escape. And the way to do that is to move right when you want to go right. That's a super simplified idea, but you can see here that the attractor landscape on the right side for the horizontal neck muscle is more symmetrical than the left one. It's because the ball that the robot was following is subject to gravity. So the space for which the robot has to go, the sensory space for which the robot has to go up is smaller than the ones that it has to go down. So that is also represented in, so the environment or the physics of the environment also becomes slowly represented into the bodies themselves. I have 5 results about this that I want to talk about, and then I'm going to stop. We can also go to the bathroom, and then we resume with some more reservoir ideas. 5 lessons from this. First, that projections of attractors to motor space, they become actions, just like in the case of the insect gate. Then, the attractor landscapes, they evolve for some negative feedback for the environment. That is, it wants to look where the object is, and if it is not looking there enough, it has to reinforce that activity. So it has a negative feedback. If it overshoots on one direction, it has to go to the other direction. There is an implicit mapping of the environmental asymmetries. That's not the right picture. That actually should be this picture. The implicit mapping of the environment is the fact that the areas where you have positive and negative for the vertical are asymmetrical. So don't. The coexisting attractors account for ambiguity resolution. Okay, so this is a morphing attractor. Ah, so I just want to show you the picture. So this is an attractor that changes in the motor space as a function of the stimulus dimension. So it's basically changing a limit cycle for attraction, and what you see here is that it starts as a fixed point for certain values, and it goes to another fixed point for other values. Don't go too much into detail for this, but you know, you would be incomplete if I didn't tell you this. And this is the last one. When you have different evolution processes, you have different you start the evolution from scratch a couple of times, okay? The pictures that emerge from the attractor landscapes have to converge to the necessities of the behavioral problem solution. What's the behavioral problem? Follow the ball. How should your attractor landscapes be? Well, you have to center the ball in your field of view. The attractor landscapes over time, they converge onto these pictures, onto an asymmetric picture for vertical and horizontal, for vertical, so from up and down motions, and for a symmetrical picture in the left and right motor control. I can understand if you didn't understand every aspect of this, but what I wanted to get across is that if you're evolving to a specified functional behaviors, such as foraging, such as finding food, such as following a chemotactical gradient, the space of possible neuronal solutions is high because you can use many different kinds of neurons, but the types of behaviors that you have to display are not. So the behaviors are constrained with respect to evolution. The functional behaviors are well-defined sets of actions. And because there's well-defined sets of actions, the types of neural networks that are able to solve those functional problems are similar. Done. Sorry if I was going too fast here. I wanted to share this this small recurrent neural network through evolution idea, in which you can look into the behavior and dynamical behavior of every single unit. And in order to understand what the network's doing, you have to make assumptions about meaningfully what are the functions that it is exploiting. That's also why in the beginning of our course I make a lot of I put a lot of emphasis on the idea that to know what a neuron is doing, you have to give the neuron some sort of meaningful behavioral paradigm or meaningful stimulus. If you present visual noise to a system, you cannot measure what it actually does. You have to constrain it to a certain set of behavioral functions so that you can exploit what's the anatomy, what's the meaning of the anatomy and the neuronal dynamics. Done for this part. So small neural networks can control robots. You can evolve them. Questions? And then we can have a physiological pause. 1.5 hours.